The local ACE integration server shown has two REST APIs secured by HTTPS. The Customer API and Loyalty Card API can be used to discover information about a fictional supermarket and its customers. Customer API offers 5 methods, but we're particularly interested in the GET operations to retrieve all customers or a specific customer using a customer ID. Not all customers are members of this store's loyalty program, so the Loyalty Card API provides function to query which customers are registered. Opening the ACE Web UI, we're going to start by trying out the REST APIs, and after this we'll move to the Designer Authoring tool to show how to quickly create flows which can invoke these APIs. Retrieving all known customers, you'll see there are 3 customers who coincidentally happen to share names with famous ex-Tottenham Hotspur footballers, Harry Kane, Gary Lineker and Jimmy Greaves. Each customer has a unique number as its ID. The Loyalty API operates in a similar way, except when we query the customers registered, we only receive 2 responses for Harry and Gary. It looks like Jimmy hasn't yet signed up for the loyalty program. Switching to the Designer Authoring tool, we're going to build a scenario around invoking both the Customer and Loyalty Card APIs. After providing the Vault key to log in, we will create a new REST API flow in just a moment, but we'll start by running a discovery process to teach Designer about the 2 APIs we wish to invoke. The Applications and APIs page loads a catalogue of available back-end third-party services which we may want to connect to. There are previously configured accounts for MQ and Salesforce, but we're going to click the New button with the plus symbol to add a new API. We're navigating the file system to locate the OpenAPI document for the Customer API, and on clicking the Next button, the document is read and we can see the available objects and actions that it contains. As you'll recall, the Customer API has 5 operations in total. When that import process finishes successfully, the Customer API will now be listed in our catalogue. We're now going to repeat that process for the second API representing the loyalty card information. The final flow which we construct will invoke both Customer and Loyalty APIs in that order, using the same customer identity in order to figure out their current overall status. Clicking the blue button to import the API finishes the import process. The resulting APIs are now added into the catalogued list of available endpoints, and whilst we've provided a definition of how the APIs operate, we haven't yet provided any connection information to the system where the APIs are actually hosted, which is exactly what we'll do next. There are options to provide a username and password, but we don't have basic authentication turned on in this simple example, so we can ignore those fields and complete the connection. The connected applications now include the Customer API alongside MQ and Salesforce. We're now going to navigate down and repeat the process for the Loyalty Card API. The only change we'll make here is to, again, repeat the setting to allow self-signed certificates, and then hit the Connect button, and we've successfully connected the Loyalty API as well. For this reason, you can now see there are 4 connections in our connected list. We'll now start the process of creating the actual flow, which will exploit the 2 connections we've just made. We're going to create a flow for API which requires us to have a model to describe the inbound-outbound data. We're going to call this our supermarket customer model, and we're going to pass in a customer ID to uniquely identify the customer that we're querying. We're also going to have a message property which will provide some response information. We're going to implement a flow for one of the actions against this model, to simply retrieve the supermarket customer by ID. Adding in a REST request option, we're going to select the Customer API, and in the Where clause, we will pass in the customer ID that came into the initial query that drives this whole flow. We'll then add a second Loyalty Card API REST request, and this time when we navigate through to the action, we'll repeat the input value from the request URL parameters containing the customer ID a second time around. The last job in our flow is to take the information from both of those 2 REST requests and include it within the final output. The field in the output data called message will contain both a response from the Customer API followed by the Loyalty Card API, with 2 separate values being provided into the field. And that completes the very simple process of authoring the flow. What we're now going to do is use the designer's inbuilt function to test out that API. We're going to try a few different values. Navigating to the Test tab at the top of the page and then selecting the Get operation that we defined in the flow, we can then move to the right side of the page and select the Try It tab, where we'll have the option to provide the input data for the flow invocation. We're passing in the customer ID number 1, and examining the response message, we can see that Harry Kane has been located. He is a member of the loyalty program, has 280 points in the gold membership tier, and his home store is located in Munich. Trying out a second ID, number 2, we get very similar information back. Again, we see that Gary Lineker is also a member of the loyalty program. He has a different number of points inside the silver membership tier. The third piece of data that we'll use to invoke the flow has customer ID number 3. This time things are slightly different. Jimmy Greaves has been located as a known customer, but no loyalty card has been found with his loyalty card ID, which shouldn't be surprising given the values that we saw at the very beginning of the demonstration. The final flow invocation with ID number 4 finds that no customer exists with that ID, nor is there loyalty information either. So in conclusion, this demo has shown the invocation of REST APIs imported into the Designer authoring tool. This quick demonstration explores some usability enhancements for the toolkit in ACE 13060, which make it easier to work with policies. This demo uses an integration node, and we can see there's a variety of artifacts that have been deployed to the servers owned by that node. And in the toolkit here, we're now going to create a new policy named example policy, and we're going to select the activity log type. Within an activity log policy, you can choose the minimum severity of the log entries that you would like to be inserted in the activity log which is saved. In the file name property, we're choosing to type the name of a file that we're going to write these entries to on the disk system. Of particular interest in this demonstration is the new description section, which is now placed at the top of all of the different policy types. It consists of a version field, a short description, and a long description. In various other places, individual policy types have also started grouping properties together within twisties that look very similar to the description one that we're looking at here. Having defined our policy, we're now going to deploy the policy project to server 3, and then we're going to examine the effects at runtime. Bringing up a command console, we can run the MQSI list command with a low level of depth to recursively look within that server at all of the artifacts and their properties. We can see that version 1.0 of our policy has already been deployed, with its short description and long description copied through, and crucially, to begin with, there are no keywords associated with that policy. We're going to return to that command in just a moment, but before we do so, we're going to simulate the process of a user updating and redeploying the policy. They've now labelled it as version 2, and this time around we're going to use the $MQSI keyword syntax in order to apply an author property to this particular policy using the short description field. We can also change the description in the long description and one of the properties of the policy so that we start gathering in activity log at a different level of severity. When we redeploy the policy, we can then return to our command console and see the impact of those changes. Repeating the MQSI list command shows that now we have assigned version 2 in the metadata for the policy. We've also got the updated descriptions and now a dedicated keyword where the author has been recognized as Ben Thompson. In summary, our quick demo has shown the new description fields on policies and how to exploit them for improved admin and reporting. In this recording, we're going to demonstrate some new capabilities in 13060 for the scheduler node. In this example, we have an interval of 5 seconds set up, and on the Advanced tab, we have some further settings that show how we can now interact with a state persistence policy. The state persistence policy has a couple of alternatives. You can use a persistence type of file or Redis. In our case, we're using file, so we've provided a directory for its usage. Returning to the flow, the scheduler node has a missed event mode property, which to begin with is set to none. When we deploy the application, you can see that the flow is triggered every 5 seconds, with the compute node generating a brief message written to the output file, being tailed at the bottom of the screen. A new line is added to the file every 5 seconds. As I'm talking, we're then going to restart the integration server and watch what happens to the events being generated. The detailed entries in the file are noting the time in the compute node and the time when the scheduler node propagation actually started. Typically, these steps are a few thousandths of a second apart, and these values will be useful to us when explaining some behavior later on. Now the server is in the process of starting up again, I've manually inserted a couple of blank lines into the tail output so that it will be easy to identify what is written to the file after the restart completes. The success dialog is going to show that the server has been restarted again, and the messages will appear at 5-second intervals just like before. Note that there was a dead period whilst the server was stopped of about half a minute, from 7 minutes 44 seconds to 8 minutes 21 seconds. During this time, no new events were generated, and when the server restarted, there was no event catch-up occurring either. We're now going to amend the flow and change the missed event mode to be all. When we then redeploy this to the same integration server, we'll notice the change in behavior. The deploy takes a few seconds, but is significantly quicker than the server restart, and you'll notice that after the flow deployed, the first couple of events show a slightly larger time difference between when the flow was scheduled to start and when it was actually running. With the brief pause for a redeployment, things are quickly back on track with the 5-second interval, but we'll be able to see more clearly what's actually happening here with the catch-up of generated events if we do another full server restart. The message at the bottom right of the toolkit shows that the server is now in the process of being stopped. Once completely stopped, the toolkit will immediately restart the server, and that whole process, just like we saw a moment ago, is likely to take us around 30 seconds. When the server restarts, you should notice a sudden rush of 7 or 8 events appear in the lower window, as the integration server will attempt to catch up with the scheduled events that otherwise would have been triggered during the period whilst the server was stopped. The information we're logging should show that even though these events all occur very closely one after the other, as soon as the server starts, their scheduled start times will cover the time period during when the server was stopped. We also notice that the time difference between each event's scheduled time and the actual time of processing should get closer together as the server catches up, and within a few seconds, we're now back to normal with a time period of a few thousandths of a second between the event triggering the flow and the flow propagation recording the current time in the compute node ESQL. This concludes our demonstration of state persistence policies being used with the scheduler node.